Welcome back to Applied Physics. In this video, I want to talk about simple machines. When most people hear the word machine, they immediately conjure ideas of complicated and usually large devices. For some people, that might be something like a small engine on a walk-behind lawnmower. For some people, that's machining tools like a lathe or a mill. These are all examples of what are sometimes called compound or complex machines. These machines have a lot of moving parts that are used in order to perform the task at which they are specialized. Unfortunately, those kinds of machines are well beyond the scope of this course. We're going to stick with simple machines. We're going to try to drill down and look at just one component of one of these more complicated machines. If we can learn how to analyze each component on their own, we can then build up from that to deal with larger and larger components and get to those compound machines. And if that's something you need in a future study, that's something that you can look at further. Right, so we're going to stick with simple machines, the basics, and make sure we understand the concepts first. Before we get into any of that, though, a formal definition. A machine is any device which can be used to transfer energy applied in one location to useful work done at another location. In this view, a machine is a black box. We feed energy into it, and it spits out work. Of course, when we think about energy and work, the first thing that should come to your mind is conservation of energy. In the ideal world, the energy input into the machine should be equal to the work output by the machine. Of course, in the real world, things are never that convenient. Every machine is going to have some amount of waste, and that waste is going to take the form of energy. So any waste energy is energy that is put into the machine that does something other than the work that you are trying to get the machine to do. A couple of examples here. A lot of machines are going to generate a lot of heat from the friction of their components. Very frequently, a machine creates noise, and those are both classic examples of waste energy, energy that is put into the machine that does not get to do work. If we were interested in pursuing this, the important measure here is called the efficiency, the ratio of the work done by the machine to the energy that is put into the machine. But for the sake of getting through to the interesting bits, we're actually going to ignore that for the time being. Let's just pretend that our machine is 100% efficient. All of the energy turns into work. Although, in and of itself, that raises an interesting question. If a machine is not perfectly efficient, if it takes more energy than the amount of work you get out of the machine, what is the value of the machine? Sometimes that's a matter of who is doing the work. A lot of the machines that we have developed as a society are turning energy outside of human effort into work. From something like a water wheel to a diesel engine to electric motors, we are taking energy that is stored outside of ourselves and turning it into work. But again, that's by and large a conversation about more complex machines. We want to work with simple machines in this course, so we're just going to look at the effort that we are applying. If I am putting effort into the machine in the form of energy, I'm not getting as much work out as I'm putting in. And yet I still use simple machines every day. So instead of thinking about energy, it might be worth thinking about this in terms of force. Remember that work is equal to the force times the distance. And yeah, if the force is not being applied in the direction of motion, you have to take a cosine of theta. But let's ignore that for now and make our lives a little bit easier. Well, to get the same amount of work, we could either apply a large force over a small distance, or a small force over a large distance. If we apply 100 newtons of force over 1 meter, we get 100 joules of work. If we apply 10 newtons of force over a distance of 10 meters, we also get 100 joules of force. So that is the power of simple machines. We can drastically reduce the amount of force we have to apply to the machine and still get a larger force coming out of the machine. Right. One last bit of vocabulary here. We're going to call the effort, and as a variable, this is a force, so maybe F sub E, the force applied to the machine in order to supply the energy. And then the resistance, F sub R, will be the force overcome by the machine when it does its work. That leads us to the mechanical advantage. This is the thing that actually makes the machine useful. Very often I see mechanical advantage written as ME. That is 2 letters for one variable. ME is a single variable. It is the mechanical advantage. And it's just the ratio. The resistance force divided by the effort force. So for a machine that has a mechanical advantage of, say, 2, then for every newton of force that you put into the machine, you get 2 newtons of force out of it. If you have a machine that has a mechanical advantage of 10, and you are trying to lift a crate that weighs 250 pounds, then rearranging this equation, we get that With this machine that has a mechanical advantage of 10, you have to put in 25 pounds of force as your effort in order to lift a 250-pound object. Again, you can't get something for nothing, so you're going to apply that force over 10 times the distance that you need to lift a machine, but honestly, I'll take that trade-off. Lifting 25 pounds is not particularly difficult. Lifting 250 pounds is a point where I'm liable to hurt myself. So there is the power of simple machines. Physicists classify 6 different types of simple machines: the lever, the wheel and axle, the pulley, the inclined plane, the screw, and the wedge. Every machine that is possible to be made is a combination of these 6 machines. Sometimes there's a lot of combinations of these 6 machines. Right? Most of the machines that we deal with in our society have hundreds, if not thousands, of parts, but each part can be analyzed as being one of these. I'm going to actually simplify this list a little bit further. We're going to, in this video, look at the lever, the pulley, and the inclined plane. If you squint and tilt your head a little bit, you can actually convince yourself that the wheel and axle, the screw, and the wedge are each special cases of the inclined plane. So once you understand these 3, understanding the other 3 is fairly straightforward. Of them, I think that the inclined plane is the most straightforward, so we'll start there. A side view. An inclined plane looks something like this. You have a box sitting on a ramp. You apply a force along the ramp in order to apply the effort, but then the resistance force is gravity, which is pointing just downward. So when you think about it, your real goal of an inclined plane is to raise a box. It was on the floor, and now it is some height above the floor. In order to do that, you are going to push the box along some distance. And if the angle is small enough, then it doesn't really matter if we measure the distance that way or that way. It should come out to be about the same value, to within the approximation we care about. So we're not going to squabble about that. You'll see the differences showing up. Right? But we know that work is force times distance. So, assuming 100% efficiency, assuming that nothing is lost to friction, heat, sound, anything else like that, then the force of effort times the distance along which the effort is applied should be equal to the resisting force times the distance along which the resistance is applied, which is the height of the ramp. And if I just play a bit of a rearranging game, divide both sides of this equation by h and by fe, then we get that L over h is equal to Fr over Fe, And remember, Fr over Fe is the mechanical advantage. So the ratio of the distance across the floor to the distance that you're trying to push upward is the mechanical advantage. If we have a ramp which goes 1 foot across the floor to go up 1 inch, as an aside, this is the ADA requirement for a wheelchair ramp. For every 1 inch the wheelchair ramp has to go upward, it should travel 1 foot across the floor. Well, 1 foot is the same thing as 12 inches. So the mechanical advantage of this ramp is 12 inches over 1 inch, which is just 12. And now let's consider a person in a wheelchair. A person with wheelchair might have a weight something like, let's go with 200 pounds because it's a nice even number. Well, that weight of the person and the wheelchair is the resistive force. That is how much stuff we want to raise up this distance. We just figured out that our mechanical advantage is 12, and then the question is, how much effort does it take to push this 200-pound weight of a person in a wheelchair up a ramp? Well, mechanical advantage is resistive force divided by effort force. Rearranging that, we get that effort force is resistive force divided by mechanical advantage. Plug in what we know. And instead of having to lift this 200-pound person in wheelchair up directly an inch, we have to push them a foot, but we only have to put in 16.7, shy of 17 pounds of effort in order to do so. Once again, in the real world, we also have to take efficiency into account, because as you're pushing someone, even someone in a wheelchair, up a ramp, there is going to be friction. The wheels are going to rub on the wheelchair. The wheels are going to rub on the carpet. There's going to be some slipping, and probably something is going to squeak. So you're going to lose some energy, which means it's going to take a little bit more than just that amount of force in order to overcome everything. But it's a very good starting point. And for our purposes, that's going to be good enough. We're going to ignore all of the problems with friction and just assume that things work nicely. We have a perfectly balanced wheelchair that is more than capable of supporting the weight of the person sitting in it, and so we are happy to ignore friction entirely. Up next, let's take a look at the pulley. A single pulley is probably the most boring of all possible simple machines. You can use a pulley by mounting it to a fixed surface and attaching a rope so that you have some load. The resistive force is going to be the gravity pulling down whatever thing you are trying to lift up, and you're going to achieve that by applying effort along the string in some other location. When you have a system with a single pulley like this, the pulley just acts to redirect the force. There is no mechanical advantage. in this setup. In order to get a mechanical advantage, we need to adjust the setup a little bit. So instead of having our string directly attached to the object we're lifting, the interesting thing to do is let's attach another pulley to that object so that our string loops through that pulley and then back up. And now, the resistive force gets spread evenly across the two strings that are attached downward onto that load, and the force is half of what it might have been otherwise. Fe now equals 1/2 Fr, because again, this pulley is just redirecting the force on this bit of string, and then this pulley is redirecting the force on this bit of string, so that it's just half of the force that it was before. And of course, now we're going to be moving twice the distance because we have to shorten this bit of string and that bit of string by the same amount. So we have to go twice as far to shorten each of the pieces of string, but we can apply half as much force. And the mechanical advantage in this case is 2. We can get even more complicated. Here I have several pulleys, 2 pulleys attached to the ceiling and 1 pulley attached to the object. The interesting thing that happens here is that the more pulleys you have, the more strands you have that are supporting the weight of the load. It can be a little bit confusing sometimes to figure out how many strands are actually supporting the load. Right? In this case, the strand over here, this is the one that you're going to be pulling yourself. Well, that's attached to the pulley up here, but it's not really a line connecting to the load, so it doesn't count. In this setup, the mechanical advantage is 3. Compare that to this setup, where apparently you are above the attachment of all of the pulleys. And we've got a pulley that is attached, or I'm sorry, we've got a string that's attached to the load, loops up through a pulley, down through a pulley, up through a pulley, down through a pulley, and then up to where you are pulling it from above the entire setup. Well, in this case, there are, 1, 2, 3, 4, 5. This cord is directly attached to the load and is helping to support the weight of the load. So the mechanical advantage in this setup is 5. All right, one more machine to talk about here, the lever. A lever is a machine comprised of 3 pieces. The most important piece is a pivot point, which we call the fulcrum. And then there is some sort of a fixed arm that can pivot on that fulcrum. In this orientation, we have an effort force pushing downward, and then presumably there is some sort of a load applying a resistance force on the other side. The distance from where you apply effort to the fulcrum is called the effort arm. And then the distance from the fulcrum to where the load is balanced is called the resistance arm. And then the mechanical advantage is the distance on the effort arm divided by the distance on the resistance arm. Some of the confusing things about fulcrums are that the lever doesn't have to be a straight line. In fact, one of the most common levers in existence is the crowbar, which is kind of shaped like this, so that it sits on the ground. Your effort arm is bent that way. Your resistance arm is bent the other way. And even though it's a bent shape, it is still a lever. The other thing that tends to be confusing about a lever is that the resistance and the effort don't have to be on opposite sides of the fulcrum. If we set up a fulcrum on one side and we attach a load somewhere a little bit up and then apply effort a little bit further up, this is still a lever. And if you think about it, you should recognize this lever. It might make a little bit more sense if I put a nice wheel here and I make this load a little bit larger. What I've really just drawn is a wheelbarrow. Right? Put a couple of legs on it. But it's still a lever. The fact that the load and the resistance are on the same side makes no difference. But we can measure the distance from where the load is applying resistance to the fulcrum. That is still not FR, that is LR. And we can measure the distance from where we are grabbing it to the fulcrum. That is still LE, and nothing changes even though the configuration itself has changed. You may see some sources refer to the different configurations, the different orientations of the effort, the resistance, and the fulcrum on a lever as class 1, class 2, and class 3. I'm not that worried about the vocabulary there. I just want you to understand the essence of the mechanical advantage. Right? Just take the ratio of the distance across each of them. That gives you your mechanical advantage. I think this video has gone on long enough, so I'm going to wrap up with that. As always, thank you for joining me, and I'll see you next time.